So in this lesson, I'm going to work through ionic equations where there's a precipitate that forms. So the first step is to be able to look at what reactants you have and break them down into cations and anions. So in this case, looking at the periodic table, I know that mercury is a metal, and I can see that in the periodic table. I know that it will have a plus charge. I'm not exactly sure what charge that might be yet, because sometimes the metals in the first and second column don't have set charges, but I do know that I have a nitrate. In fact, for nitrate, I look at my polyatomic chart and I know it has a -1 charge. I notice over here the subscript tells me I have 2 nitrates, so I'm going to place 2 nitrates in the front. So if that's the case, if I have 2 nitrates, each of them with a -1 charge, and remember I need to have those charges equaling 0, I'm going to determine that mercury actually has a +2 charge. And I do that by sort of the back door, seeing that I have 2 nitrates that have a negative charge. So how can I tell the difference between a cation and an anion? Why am I not separating the nitrogen and the oxygen apart from each other? And this is where you use your polyatomic chart. Look for those, anything that has an oxygen usually at the end is going to be one of the polyatomic atoms. So we're going to place aqueous on there because they are dissolved in water. And I'm going to actually draw what that looks like right underneath here, just so that you get a sense. Actually, maybe I won't. I'll do that in a little bit. So the next chemical formula I have is K2S. I look at K. K is in that first column, and it tells me it has a plus charge. And I'm looking at the periodic table. I have 2 of those. So for that reason, I'm going to place the 2 in front for right now, and then S, looking at the periodic table, is a -2 charge, and I write down aqueous. Okay. So this is the first step, is breaking down those cations to anions. So essentially what we're going to do when the actual reactant happens is that you're going to come up with different combinations. And so this is where I actually like to draw what it is that you should see in your beaker. So in this case, you have mercury. We have 1 mercury in here, so I'll just write Hg with a +2. And it looks like I have 2 nitrates, so that's NO3. Each of those has a -1 charge. And because they're in water, they've disassociated and they've dissolved, and water is more or less surrounding them. So this is what we've done last class, or the last weeks. So those are my water molecules that are actually surrounding them. Okay? So I also have 2 Ks. Each has a positive charge. So there's 1 K, there's another K, and it looks like I have 1 S. And that has a -2 charge. And again, those are also all dissolved in water. So they've all separated. So what possible combinations can we come up with that are new combinations? Well, you know that the positive charges are always attracted to the negative charges. So mercury right now was attracted to the nitrate. It's dissolved. And we're going to now see if it is attracted to this possible combination of Hg +2 with the sulfur, which is a -2. So we have the pluses and minuses. So I'm going to just write this down right now and now double check whether or not my charges work. So up here, just as a note to myself, mercury has a +2 charge. I remember that from over here. Sulfur has a -2 charge. That actually works out to be 0. We can keep them as a 1-to-1 relationship. All right, so the next thing is seeing the other combination. Okay, so I can say that potassium and nitrate combine. So KNO3. All right, so let me look at those charges. Remember, potassium has a plus charge, nitrate has a -1 charge. Those also work out to be pretty much working out to 0. So I know that 1 potassium is going to bond to 1 nitrate. But I have, how many of them do I have here? I have 2 sets, okay? So in that case, I can place a big 2 over here, and I've then balanced the equation. So I'm using my drawing to sort of figure out what's happening. There's a quick way of doing this also. You can just swap the first cations with each other. So you place the Hg over here and the K2 over here. You have to make sure your charges work out to be 0, though, in all of them. Okay. So the next step in this is determining which one of these is going to be a solid. And so in order to do that, you're going to use your solubility table. So in my solubility table, the first thing I'm going to do is look for Hg. It looks like Hg, I spot that in the exception rules, that whenever it's combined with a chlorine, bromine, or iodine, that it actually becomes solid. It's not combining with chlorine, bromine, or iodine, so this one might not become a solid. But let me make sure that the sulfur is actually something that's soluble. So I keep on looking. So this here, I can't tell quite yet whether or not, just based on the mercury, if it's going to be a solid or not. So now I'm looking at the sulfur. And when I look at the sulfur, I look at the bottom part, and I see sulfides. It says S2, and it falls under the category of always being insoluble. So that lets me know that that's a solid. That means that the other one is going to be aqueous. And how can I tell that it's aqueous? Well, when I look at the K falls into the category of soluble compounds, and it looks like it's always soluble regardless of what you have. So next step is write down what I have. So I know HGS remains a solid, so I keep it written together. But the KNO3 are going to be aqueous, so they do not create a bond. So I'm going to erase this bond here because these stay soluble. So in my drawing, this is what it should look like. And so that means I can put 2 K pluses I have as aqueous, and I apologize that I ran out of space, and 2 NO3s that are negative, those are aqueous as well. Okay, they did not bond because my solubility chart told me that they didn't bond. So what this is called is the total ionic equation. Total ionic equation. Because it shows you the entire picture of what's going on. Next, what we're going to do is the net ionic equation. So for the net ionic equation, you're going to just focus on the ones that actually did form a bond. And you look here at your picture, and you're like, wait a second, it looks like just that the mercury bonded with the sulfur to form a solid. Nothing else did. So for the net ionic equation, you just focus on which things did bond. You're going to ignore the rest. And that pretty much works through an entire total ionic and net ionic equation.